Hey guys, welcome back to another tutorial. Today I'm going to cover A-star search. It's an algorithm used most commonly used in artificial intelligence for determining the shortest path. It's most commonly used for Google Maps and those types of applications. So today I'm going to go over a pretty simple but applicable question that is trying to get one person from a start to an end and trying to find the best path for them to take. So the question asks, use A-star search to determine the shortest and most optimal route to the target. The rules that they tell us is the cost to move to a state is shown in the respective tiles. So as you can see in the environment down here, each tile has a number in it, and that tile represents how much it costs to get to that tile. The next thing it says is the straight line cost is computed by the Manhattan distance. So we'll need to calculate this. We'll need to know the straight line distance in order to solve for A-star. So I'll go over how you calculate the Manhattan distance when we get into the problem. And then the next rule is the person cannot move diagonally or outside the map, only up, down, left, or right. So you can only go up, down, left, right. It's pretty self-explanatory. And then states with lines through them are obstacles and cannot be traveled through. So you can see these cells in the environment that have lines through them. You can just represent it like a tree or something that you can't go through, so that's why they're blocked off. So you have to go around them or whatnot. So the way we're going to solve this is by use of a tree. So we're going to have the starting node, and then we're going to follow the nodes down to find which path is the best way. So we'll start, and to distinguish what nodes are what in the environment, we can label this environment here with XY labels. So we can label them like this. Actually, I'll start with 0. 0, 1, 2, 3, 4, 5. 0, 1, 2, 3, 4, 5. And this will be Y, and this is X. So as you can see, the person right here, just marked him, that person is in node 0, 0. And we can only go up and right in this case because left and down don't exist in the map and you can't go diagonally. So we're going to go, we have two options. We can go to 0, 1 and 1, 0. So now we have to calculate the heuristic values for both of these nodes. This will help us determine which path we're going to take. So what we're going to do is for the 0, 1, as we can see, it has a 3 on that cell. So that's the cost. It costs to go to that cell. So that's part of the heuristic value. The next part we need to calculate is to compute the heuristic value is to get the straight line distance. So as I said, you use the Manhattan distance. So this is done by, it's pretty self-explanatory. All you have to do is you just can't go diagonally. So any path that gets you to the star that doesn't go diagonally. So I can just label 1, and then we can see it's pretty easy. So if we go like that, that costs 9. That's 9 cells. So that's the straight line distance. So this is going to give us 12. Let me just erase this. And then for the other one, for 1, 0, it as you can see, there's a 2 on the cell, so it means it costs 2 to get to that cell. So it's 2, and then the cost to straight line distance for that one, for 1, 0, is if we do this again, it will also return us 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. So from there, the way you decide which node you travel to next is you just pick the, oops, I did not add these up properly. So sorry, this is 12, and then this will give us 11. So the way you choose is by, since this is a greedy algorithm, you're going to choose whatever is the least expensive. So as you can see, there is an 11, and 11 is less than 12, so we're going to go with the 11 side. So we're not gonna go any further with that branch. We're just gonna continue with the 1 0. So from 1 0, we can go either up to 1 1 or right to 2 0. And to calculate the heuristic values, one important thing to remember is you have to add the previous, not the heuristic value, but the previous costs of cells. So I'll show you. But for this one, it costs it costs for, for 1 1, it costs, as you can see on the cell here, it costs 1 right here. It costs 1. So 1 plus the previous cost of the cell where we came from was 2, because we came from this cell right here. So you add that to it. And then you add the straight line distance. So the straight line distance from here is 1, 2, 3, 4, 5, 6, 7. I believe I computed that wrong. Let me just try that again. 1, 2, 3, 4, 5, 6, 7. Oops. One, 2, 3, 4, 5, 6, 7, 8. I believe it's 8. We'll go with that for now. I'll change it if there's a mistake. So that gives us 11. And then the other one is 2 0. 2 0 is the cost to get onto that cell is right here, and that is 2. And then the cost of the previous cell was 2. And then the straight line distance is 1. Actually, I'll go the other way. 1, 2, 3, 4, 5, 6, 7, 8. So it's also 8. And that will give us 12. So we're gonna pick the shortest cost again. So that's gonna be 11. So we'll go with this one. We'll go with 1 1, and we're gonna continue this process. And the one thing to keep in mind is you just gotta keep adding all the previous costs of the cell that you've taken, as well as the straight line cost from whatever cell you're on. So the heuristic value will increase, most likely, but we'll see it through. So I'm going to speed this part of the video up. I'm going to complete it, but I'm going to speed it up and just do it manually, and I won't be speaking, and then I'll reconvene at the end. So if you have any questions on the solution, so the solution would just be following each node. So it would be as the path outlined here. You can just represent that as the xy values and show which after each xy value where the next xy value is. And that's the path that would be the solution. And that's the most optimal path that's solved through A star search. So if you have any questions, leave them in the comments and I'll try to get back to you. And yeah, thanks for sticking around. Peace.